Many industrial processes depend on the controlled use of heat. To better understand the vital role that heat plays in the process industries, you need a good grounding in the principles of heat and heat transfer. One of the problems in understanding heat is that you can't see heat directly, but you can see the effects of heat. One effect is seen on this thermometer. The temperature is rising, indicating that heat is being added to the water. Here's another example. This container is filled with air, a gas. Connected to the container are a thermometer and a makeshift manometer, which indicates pressure changes. When we heat the air in the container, there are two main effects. One effect is an increase in temperature. The other is an increase in pressure. As the air's pressure increases, it pushes the liquid in the manometer, changing its level. In the two examples we just saw, the effects of adding heat were obvious, changes in temperature and changes in pressure. The addition of heat caused a change in the properties of the substance. Another possible effect of adding or removing heat is a change in the state or phase of a substance. All substances exist in one of three phases of matter: solid, liquid, or gas. If we heat ice, a solid, of course it melts and changes into water, a liquid. So adding heat has caused the ice to change its state from a solid to a liquid. Then if we heat the water, it boils. So the heat causes the water to change its state from a liquid to a gas, steam. The effects of heat are all related to changes in molecular motion. For example, when heat is added, the motion of the molecules that make up a substance increases. When heat is removed, molecular motion decreases. All solids, liquids, and gases are made up of molecules, and these molecules are constantly moving. Since molecules are always moving, they have kinetic energy. Kinetic energy is the energy of motion. One way to measure kinetic energy is in terms of temperature. Basically, temperature is the degree of hotness or coldness of a substance measured on a scale. As you know, temperature scales usually indicate units of degrees Fahrenheit or degrees centigrade or Celsius. At the molecular level, temperature is a measure of the average molecular kinetic energy of a substance. That is, temperature is an indication of the average molecular motion in a substance. Another way to look at temperature is in terms of intensity. The faster the molecules of a substance move, the more intense the motion is. The greater the intensity, the higher the temperature. Although the molecules in a substance are always moving, some molecules may move faster than others. Boiling water illustrates this principle. With boiling water, some of the water molecules move fast enough to overcome the molecular forces holding them together. When water boils, some of the molecules move fast enough to escape the water as steam. In general, boiling can be defined as the condition at which the molecules of a heated liquid become active enough to escape the liquid. In the case of water, the temperature has to reach 212 degrees Fahrenheit to cause the molecules to move fast enough to leave the water as steam. At this point, we'll turn our attention from temperature to heat. Heat is a form of energy called thermal energy. In a sense, heat is the amount of thermal energy, and temperature is the intensity of the thermal energy. We'll use two beakers of water to illustrate the relationship between temperature and thermal energy. This beaker has only half as much water as this beaker. The temperature in the beaker with less water is 110 degrees Fahrenheit. The temperature in the beaker with more water is 100 degrees Fahrenheit. The beaker with more water contains more thermal energy and therefore more heat than the other beaker. Because there's more water, it takes more heat to raise the temperature of this water than it takes to raise the temperature in the beaker with less water. Although the beaker with less water has less thermal energy, its energy is more intense than the energy in the beaker with more water. The average molecular motion in this beaker is faster, so its temperature is higher. The two units generally used to measure heat are the British Thermal Unit, or BTU, and the calorie. A BTU is the amount of energy needed to raise the temperature of 1 pound of water 1 degree Fahrenheit. A calorie is the amount of energy needed to raise the temperature of 1 gram of water 1 degree Celsius. Heat is a form of energy known as thermal energy. Thermal energy can be either stored in a substance or transferred from one substance to another. There's an important law of energy called the law of energy conservation. This law states that energy can be neither created nor destroyed, only altered in form. Basically, this law means that all energy has to be accounted for. There are a couple of ways the law of energy conservation works. As an example, fuels contain chemical energy. When fuel is burned during combustion, heat is generated. This heat is thermal energy. So the process of burning fuel alters the form of energy from chemical to thermal. Now let's say the heat from combustion is used to heat a process fluid flowing inside furnace tubes. Much of this heat from combustion, or thermal energy, is transferred to the process fluid. Since no furnace operates at 100% efficiency, not all of the heat is transferred to the process fluid. Some of it may go up the stack. Some of it may be absorbed by furnace equipment, but all of it goes somewhere. That is, all of the thermal energy is accounted for, so none of it is destroyed. In this topic, we covered some of the fundamental terms and concepts pertaining to heat. We looked at the effects of heat, and we saw how temperature and thermal energy are related. We also discussed the law of energy conservation. Now's a good time to try a few practice questions. A possible effect of adding or removing heat is a change in the state or phase of a substance. All substances exist in one of 3 phases of matter: solid, liquid, or gas. Basically, temperature is the degree of hotness or coldness of a substance measured on a scale. As you know, temperature scales usually indicate units of degrees Fahrenheit or degrees centigrade or Celsius. At the molecular level, temperature is a measure of the average molecular kinetic energy of a substance. That is, temperature is an indication of the average molecular motion in a substance. Heat is a form of energy known as thermal energy. Thermal energy can be either stored in a substance or transferred from one substance to another. There's an important law of energy called the law of energy conservation. This law states that energy can be neither created nor destroyed, only altered in form. Basically, this law means that all energy has to be accounted for. A temperature change can be measured or felt. Heat transfer that causes a temperature change is called sensible heat transfer. Heat transfer that does not cause a temperature change is called latent heat transfer. During latent heat transfer, there are changes in molecular energy, but these changes don't result in a temperature change. Instead, they result in a phase change. The 3 phases or states of matter are solids, liquids, and gases. So, sensible heat results in a temperature change, while latent heat results in a phase change. We'll heat a beaker of ice to demonstrate phase changes and latent heat transfer. We'll also use a graph to show the relationship between temperature and heat. The ice is melting, but at first, the temperature stays at 32 degrees Fahrenheit. Latent heat is being absorbed by the ice. The latent heat causes the molecules of ice to overcome the molecular forces holding them together. As a result, the molecules move freely as a liquid. But as yet, there is no temperature change. There's only a phase change from solid to liquid. Now that the ice is melted, the addition of heat does produce a temperature change. At 212 degrees, the water boils into steam, but the temperature stays the same. The water undergoes a phase change, but not a temperature change. At 212 degrees, the latent heat causes the molecules to move fast enough to overcome the molecular forces holding them together. When the molecules absorb enough latent heat, they leave the water as steam. Section B represents sensible heat because from this point to this point, the temperature of the water changes as a result of heat transfer. Section A and Section C represent latent heat transfer because there are no temperature changes in these sections, only phase changes. This horizontal line at 32 degrees represents the latent heat of fusion or melting. The latent heat of fusion is the amount of heat required to melt a substance without a change in temperature or pressure. This point represents ice at 32 degrees. And this point represents water at 32 degrees. The line between these points represents an ice-water mixture. This horizontal line represents the latent heat of vaporization. The latent heat of vaporization is the amount of heat required to vaporize a substance without a change in temperature or pressure. This point represents water at 212 degrees. And this point represents steam at 212 degrees. So the line between these points represents a water-steam mixture. In the example we just saw, heat was added. If heat is removed, the heat transfer line moves in the opposite direction. That is, when heat is removed from steam, the steam starts to condense into water. Under these conditions, heat is removed from steam, and the steam condenses rather than vaporizes. So this line represents the latent heat of condensation. The latent heat of condensation is the amount of heat that has to be removed from a substance to condense it without producing a change in temperature or pressure. Then, when heat is removed from water, there's a sensible heat transfer, and the water temperature drops until it reaches 32 degrees. At that point, any heat removed is latent heat, so the temperature remains at 32 degrees. This line then represents the latent heat of freezing. The latent heat of freezing is the amount of heat that has to be removed from a substance to freeze it without producing a change in temperature or pressure. When a liquid boils, a phase change occurs. A substance changes from a liquid state of matter to a vapor state. The boiling point of a liquid is affected by temperature and pressure. To show how temperature and pressure affect boiling points, we'll use water as an example. But the same basic principles apply for all liquids. The boiling temperature of water is different at different pressures. For example, at atmospheric pressure, water boils at 212 degrees Fahrenheit. But at pressures lower than atmospheric, the boiling temperature decreases. At pressures above atmospheric, the boiling temperature of water increases. To show how temperature, pressure, and heat are related to the boiling point of water, we can construct a graph. The vertical axis represents temperature in degrees Fahrenheit, and the horizontal axis represents heat. We'll use a pound of water as a standard, so the heat's measured in BTUs per pound. A BTU is the amount of heat needed to raise the temperature of 1 pound of water 1 degree Fahrenheit. Atmospheric pressure is 14.7 psia. At atmospheric pressure, water starts boiling at 212 degrees Fahrenheit. On our graph, this is the point at which water first starts boiling at atmospheric pressure. And this is the point at which all the water is boiled into steam. This line represents the amount of heat required to boil all the water. So this line represents the latent heat of vaporization. For 1 pound of water at atmospheric pressure, it takes about 970 BTUs of heat to boil all the water into steam. Now let's take an example in which the pressure is less than atmospheric. At this point, the pressure is 4.9 psia. At this pressure, a pound of water boils at 162 degrees. In addition, the latent heat of vaporization is around 1001 BTUs per pound. So when the pressure is reduced, water boils at a lower temperature. However, it takes more heat to boil all the water into steam than it takes at atmospheric pressure. At lower temperatures, the water molecules move more slowly. As a result, it's harder for them to boil and escape the body of water as steam. So it takes more heat to change the water completely to steam. Now let's look at a pressure that's higher than atmospheric, 114.7 psia. At this pressure, water won't boil until it reaches 338 degrees. Under these conditions, the latent heat of vaporization is about 881 BTUs per pound, which is less than the latent heat of vaporization at atmospheric pressure. At higher temperatures, the water molecules move more quickly than they do at lower temperatures. so it's easier for the molecules to boil and escape the water as steam. In other words, it takes less heat to change the water completely to steam. As the pressure and boiling temperature of water increase, the latent heat of vaporization decreases. There is a point, however, at which the latent heat of vaporization is 0 BTUs per pound. This point occurs at a pressure of 3,206 psia and a boiling temperature of 705 degrees Fahrenheit. This point's called the critical point. Above the critical point, water flashes to steam, but there is no latent heat transfer. Above this point, water exists as a superheated vapor. A superheated vapor is a vapor whose temperature is higher than its boiling temperature. We can draw a curved line that connects these points. This line is called the saturation curve. The points to the left of the critical point represent liquid at the boiling temperature for a given pressure. The points to the right of the critical point represent vapor at the boiling temperature. In this topic, we examined the concept of phase changes. We contrasted latent heat with sensible heat, and we looked at the effects of temperature and pressure on the boiling point of water. Let's stop for a moment so you can answer a few practice questions. A temperature change can be measured or felt. Heat transfer that causes a temperature change is called sensible heat transfer. Heat transfer that does not cause a temperature change is called latent heat transfer. At higher temperatures, the water molecules move more quickly than they do at lower temperatures, so it's easier for the molecules to boil and escape the water as steam. In other words, it takes less heat to change the water completely to steam. As the pressure and boiling temperature of water increase, the latent heat of vaporization decreases.